So of course today we will do lesson 8, but we'll finish lesson 7. During the break we'll do a quiz 3. But anyway, so let us. There's some problem with Zoom. Let me open Zoom. Okay. So let's get started. Just a very quick review of what we have done last time. The main idea of lesson 7, okay, is to talk about prediction and linear regression. And today we'll talk about a little bit further machine learning. Cool. And you can see linear regression, if you still recall, is a kind of the very basic machine learning where you are trying to select variable automatically. Okay, the built-in algorithm is designed in such a way that if the variable is not important, it will become 0. Okay, so later we will talk a little bit more other way to do machine learning, but that is the first model we are looking at. But just quickly review the method, right? So the idea of predict, idea of prediction is you don't care whether actually X leads to change in Y, but as long as X is helpful to predict Y, then we do it, right? And I think there's a famous paper talking about chicken and egg problem, right? I mean, we often have a question whether egg come first or chicken come first. And there are people who are trying to predict the number of chicken by number of egg, right? Or by number of egg by number of chicken. Then that is also that would be a way to go to prediction, right? I mean, number of egg is helpful to predict number of chicken is predict number of egg, right? But we don't care which cause what. But that's only prediction, okay? And just to recall the way we do prediction, there are 3 types, okay? One is called quantitative. We just actually measure what actually Y is. But Y is binary, there are 2 ways, okay? That's called probability. That's we do the logic or probit. And there's another one called classification, which actually tells you directly 0 or 1. And due to the design of class, we don't touch on the classification problems in our class. I don't think we do. But you can actually check out the textbook that actually tell you how to do classification. There are more machine learning method, but we are focusing on the first one, the quantitative prediction. Okay. And just remind you the prediction error is simply just the difference. And there are many ways to do this loss function, right? They can do the mean square error. You can do various types of method, okay, to select the model, right? Because different model have different, you use different form, you different variable, and how to do them, right? And the approach is we can do it is by looking at the model, whether they have the BIC or the AIC or the R square. And you will also do what we call the validation approach, okay? We will be looking at using the training data set to train your parameter, train our model. And we look at our test sample to look at the BIC R square, okay? And there's some problem with validation because of we just use one set of training and one set for test, but usually we will do the K-fold cross validation, right? Where look at MSE, you divide the data into cut it into 25% or 30%, right, for a test set. But you randomize over this test set, they actually come up with for each model, right, the column model, model 1, model 2, model 3, and up to model K. Each model will give MSE, and each way you split the sample will give one set of MSE, right? So you have 5 different sets, then you have 5 different MSE for each model, and average of this MSE will be the performance of the model, right? And do note that each time you fit very differently, right? Because each time the training set will give you a different parameter, right? So you pick up the one that the lowest, okay? That's how you choose, okay? And for prediction process, there are many things you have to be careful, right? How to define Y, how to select the sample, how to choose X, so and so forth, right? And I think this is the table that I mentioned, right? You have the original data and live data, right? The original data is where the data you have. The live data is the data that actually you use it for production, right? Use it for your calculation. And here actually go back to everything, just go back to the before, right? How you choose Y, level or log, right? And the functional form, how you're going to choose, right? All these things are actually combined together. And here is the example, use Airbnb. If you recall, they come up with 8 different models, and you can see they do it, building it from a bottom-up approach, right? You just starting from the most simplest model and then just keep building up the stuff, okay? I think more complexity here. And how they do is look at the overall the model, they look at the BIC, look at the training, and the test one. This is the just do average, right? And then look at how then you pick the right model, right? Look at this, it's like somewhere in the middle, right? Is the lowest, right? And the last one we learn, I guess, is the one of the most important one that probably you don't learn in undergrad, right? Is the LISO, right? Which essentially asking you to the algorithm to directly select X, right? Just to remind you how they do that is it is simply a regression, okay? But you're still estimating the same model, right? So the first line is the same model you're estimating, but the way you estimate is not just minimize the vertical distance, which is you do regression, but you have additional term, right? This term actually serve for penalty. Make sure that you don't have a very large coefficient, right? You try to make sure that coefficient as small as possible. By doing so, okay, you are reducing the number of coefficient, right? Of course, some of you may ask, if I don't use absolute value, you actually square. Actually, there's something like this as well. I think it's called the ridge regression, but you can use square. But I think the textbook use LISO. And this is the lambda is not what you chose, right? It's given, right? For any given lambda, if lambda is 0, standard regression, right? If you choose higher lambda, then the coefficient will shrink very fast, become 0 very fast, right? Suppose this lambda go to very big number, and that means that you want everything to 0, right? Because this is important, okay? Do note that beta 0 is not there, okay? So beta 0 is not. So if the lambda is very big, okay, then every coefficient will become 0, right? You go back to the standard model of yi is predicted by y bar, right? So this parameter is controlled by you. And of course, you probably ask, how are we going to select the appropriate lambda? Usually we will do today we'll do a little more. It's called the search approach. We just fine tune the parameter by choosing different lambda, okay? And so that to minimize, say, the root mean square error, okay? you have to pick up the one by looking at for each possible lambda. You can calculate the model and calculate the accuracy of the prediction by looking at the root mean square error and choose the lambda that actually the best. That is the one we use. Okay, and that is the way, right? And I think we cover how we do the LISO. Just to remind you how we do it. The easiest one is use the stat model. Okay. Okay, API SM, and this is the equation that we'll be doing. And alpha is is a lambda in these slides. Right? So how big is the thing? I use 0.1, but you can use 1, 2, 3, 4, 5. Any number is fine. And here's L1 WT equal to 1 is use the absolute value. If you change to square, that will become a square. Okay, because is here, right? This guy. Okay. If you make it square, that means that you want to you actually want the coefficient to be more even more spread out, right? Because you are penalizing last coefficient. But I think current one will be fine. I don't see any particular issue. Okay. And you can see the output will look like this one. The constant with the largest, but the main thing is once you do that, actually this one becomes x3 becomes 0, right? If you run regression, you don't have x3, you still have something. So that is the idea, right? Automatically, basically, the model tell you that you can basically drop this guy, right? Just use x1, x2. Okay? It's the model tells you this it be dropped. So this is what the learning part goes, right? It's not you decide which one to drop. Is you have a mechanism or you have the rule, you have the algorithm that you run it drops automatically. So that is what the machine learning, what the learning, I mean, it's implicit, but the learning goes in here, right? So that's why I said, I mean, after last class, you can put your CV, you know, machine learning is because of this machine learning, this learning goes on here. Of course, you would say it's very simple, but that is what it is, right? It's starting to learn, right? This is only 1 and 2 is useful for prediction. 3 I can just go away, right? If you imagine if you run a regression, it's very unlikely that becomes 0, right? But in this model, you see this actually is 0. Because when we do human learning, how we do it is run a regression, right? Look at the t statistics, right? Whether p-value less than 5% or more than 5%, then that might guide you how you do it, right? Or you look at the BIC, AIC, you learn it, you do it by yourself, right? But now we are going to say, okay, this is pick directly, right? Not we look at different model, we choose one to pick, right? Because remember how we do selecting model is here, right? We look at this model, right? And we look at the cost validation result, right? And we decide how many coefficients to include. This is your decision, right? You use your eyeball to pick human learning, right? But here you can imagine this is machine learning, right? It's a machine tells you which one to pick up. Is that clear? Okay. And later we'll talk about later today, right? Here we still have to pick what is the functional form. We have a regression here. And today we talk about the regression tree, which we don't even specify this guy. Okay. This will be something determined by the model as well. Okay, later you will see. But that is we are letting the computer to choose more and more stuff. Okay. Basically, you just give them the model, he will just come up with something. Okay. So the lesser decision you're making the machine to decide what to do in the model. But we'll go to it very soon, but later. Okay, very soon. This is the goal of relearn. Okay. And in this, I talk about 2 ways to choose a lambda, right? It's a 2 way of search. One is called the grid search, right? Grid search is basically you give them what are the parameter space, you just try to do it one by one. It's called a grid search. It's just like how you do, right? Is you go to every possible value, calculate, It's very still, but it's brute force, right? So, for example, how you go, say, suppose you go to the Shanghai marriage market, right? Everyone knows Shanghai marriage market? No. This is very interesting. I wonder why no one knows. People's Park, no People's Park? So this is this marriage market, right? And there are many posts, okay? So how can you know which one is good, right? Then how do you search? Then one way to do it is look one post by one post by one post. What post number one? Okay or not? Two, okay or not? So on and so forth, right? Then it's a grid search, right? You go to one by one. So search lambda one by one, and each lambda you calculate the root mean square error, and that's you pick, right? Or whatever metrics you're looking, right? And the other way around is to we call the randomized search, right? It's the fact that the market is too large, right? I mean, there's no way you can actually go post by post, right? And then what we're going to do is you close your eye, okay, and have a random number, okay, and pick, okay. If you do enough random number, then it should be fine, okay. I mean, there's some way to randomize, but we just can go close my eyes to do it. Of course, there are many methods that make a randomization more efficient, but we just trust it, and that is the way we do. Okay, and there are a lot of numerical methods. If you learn the Newton method, there are a lot of greatest gradient method. But I'm not going to talk about those. But just you take the randomized is the one that able to solve your model when the search space is very large. You can do it. Okay, it's not our although you're IT manager, but I don't think you need to know the algorithm behind. Okay, but there's some way to do it. I guess unless you do very big data, you can do the grid search, no issue. For the thing you can run in your computer, I think the grid search is fine. But if you're thinking about running thing that is big data, or then you have to do the randomized search. And for LISO, it's not an issue because you're just maximizing only single parameter lambda, right? If you anyone who learn numerical analysis, you notice that what we call the curse of dimensionality, right? If you try to maximize more than one dimension, then things quickly become unmanageable, right? If you have multiple parameters to maximize, that's very difficult, right? Suppose you're thinking about maximizing over a line, you pick up a point on a line, that's very easy. But if you pick about a plane, and picking a point in an area is even more difficult. But if you're 3 dimension, that's very hard already. Or even 4 or 5 dimension probably is impossible to do anything, right? Because the power of multiple, right? And anyway, that is why randomized search is not a big deal. It's not, we probably don't need it for LISO, but later you will see when we do later part, regression tree, then probably you will care. And one thing we'll look at is the y hat plot. Okay, is you put the y coordinate is the y, and the x coordinate y hat is predict one, right? And they just try to see if everything fall on the 45-degree line, that's good, right? But if here you have a bunch of numbers here, then it means that those who actually high priced, the model underperform because they predict so low. Okay, so that is usually you look at this and to see whether your model do well or not. So basically you look at this and then you say, okay, if they predict the price for the expensive hotel is missing there. Okay, I mean that makes sense because this model is hotel or Airbnb, and usually there's some hidden thing you didn't capture from the Airbnb post, right? Maybe some historical relevance or there's some special thing is not there. So it's very normal that is the outline lies here rather than somewhat below, right? You don't see this, right? Most likely this one, right? So it's and it's here but not here, right? So I think that worth from economics you can understand this. Okay, and here they plot it with the predictor interval band, right? So just here you plus minus 2 SD, right? That's how they do it. And they try to distinguish depend on how many people going to live in the Airbnb, right? This is the price prediction. And this model looks very bad, right? Because for one person, you predict the price become negative, right? So, but whether you like it or not, I don't know. But this is what they have from the data. Okay. And finally, this last slide I think is also important. Is you think about external validity, and very often when we do prediction, there's a trade-off, as I said, overfitting and underfitting, right? And especially overfitting, because you IT manager, you have so much data, and you tend to use them, and usually the problem is the data look very nice when you within sample, but out of sample, when you put the live data, is also problematic because overfitting, right? You just overinterpret the special feature that happen to be appear randomly in the data. Okay, so that's why, as you said, usually you pick a simpler model. Okay, and that's why the BIC or other measure would try to say, okay, whenever it's easier, then you pick the simpler one. Don't pick the more complicated model. That's why when we learn stuff, and regression is always very good. And also I mentioned to you last time, right? When you try to predict the future, like the stock market or exchange rate fluctuation, right? Turn out to be the time series model, the simplest, the AR1 or AR2 model actually outperform most of the predictor model. Okay, so while you learn so many interesting things, then might be turn out that even though you use simple model, use OLS, do the prediction can be better. Okay, need not go to very fancy, because fancy model actually is slow and is also difficult to interpret, right? Because you run the Lyso regression, it's not immediately clear what do you, I mean, you run the regression, run the Lyso regression, right? And already there's some interpretation problem, right? Although it's still saying, okay, X go up by this, Y go up by, say suppose X1 go up by 1, Y1 would be expected to go up by 1, right? That's a model you estimate, but do not have the same flavor as regression, because this line, okay, need not pass through X bar, Y bar, right? Remember, regression, it always passes through the center of data. But once you are fitting in this kind of penalty, it's no longer clear what do you mean by those. So R square is not really well-defined problem. I mean, all many things are not very well-defined once you have those. And OLS has a very clear interpretation, right? On average, what happened, right? Because your model is not minimizing vertical distance, okay? Then everything is biased, not consistent. There are a lot of issues there. But of course, you're doing prediction, you probably don't care about those stuff. But still, I mean, this one is still good. I mean, you're still saying that, I mean, interpretation is like, okay, I still just minimize, but I just take care of the coefficient. But when you have more goals, then it's become increasing and clear what's going on. Okay. But I guess I hope I give you the idea what we're doing. Okay. So if no question, then I go to lesson 8. Okay. And the goal of lesson 8 is trying to talk about two things. Actually, as you see here, is regression tree and random forest. Okay. And possibly if you would this is most common model when you try to do predicting continuous y, right? When y is continuous. And y is discrete, that will be, I think, covered in topic 17 and 18, which is out of our scope due to the limitation of time. But you can, if you want to look at those, you can check it out. But we only focus on regression tree and forest, okay? Random forest, okay? And they belong to the chapter 15 and 16 of the book, okay? You can take a look. And the goal is teach you how to do it, okay? And some intuitive idea why they work and what are they, okay? So let me. Can share the screen, yeah. So let's do the machine learning part, okay? So if you do regression, as you remember, you have to make many decisions. Basically, we have to saying y is linear to x, right? And we have to decide the functional form is x squared, log x or log y, right? And we decide what are the models that you are choosing, right? You have to choose model 1, you have square, model 2, you have log, model 3, you use x, y, z, model 5, you have many other things, right? You have to make decision. And then you pick the best model, right? You have to decide what is the best model based on the, you choose the matrix, right? You choose BIC, R square, log loss, whatever you like. I mean, you have to pick, okay? Everything you have to make decision, okay? And if you do LISO, you delegate it to the machine to choose the best model, right? The model, by picking the lambda, you only indirectly choosing a lambda, the beta will be chosen by the software, okay? You are not choosing which best model, but you still have to choose what are the variables you include, right? The biggest set, right? You have to still tell them the functional form, whether it's square, because you run the linear one, right? You're still choosing the functional form. Of course, the set of the model must be linear, right? Still, you have a restriction on what kind of model you're running. It's a linear regression, right? And machine learning, in general, what you're actually doing is just you select what might be the variable you want to include, okay? And that's it. The rest will be done by the machine. Machine will choose what are the models, what is the best model, okay? So you can say it's a lazy way to do things, right? Just click and done, right? Just like an app, right? Just, okay, I need this. Okay, tell me the answer, okay? And in some sense it's easier, right? Because you don't need to worry about things, just done, right? Just someone do it for you. And of course, that come with a cost of doing it, but later we will see what is the problem. The main problem is you do it and there's a black box. You don't know what does that mean. It's very difficult to interpret because it's a black box model, because you don't do anything, right? You don't make decisions. So how the machine do decision, you don't know. Okay, it's complete darkness. But anyway, let's talk about the procedure. Okay, and the procedure is not too much different from what we're doing for the LISO. Okay, basically you have the data set. Okay, and you cut out some of data. Okay, one set of data is training set, the other one is the testing. Okay, and what you do is you do a k times this k for validation, right? K time to train, okay, and then you test it, okay, and usually we use loss function is we use the MSE, right, the prediction error, right, for each y minus y hat and square in some of them, and average of those, and you set the best model, okay, and they just do it on the whole thing and then evaluate performance. So this is the standard approach. Don't worry, this everything will be you will see that in the Python code. Okay, so I don't think you need to worry about the procedure, but rather you see the code and you see how we do it. Okay, and there are many methods. Okay, in machine learning, right? I think in our class we own, I think mainly two. Okay, we'll talk about two more, but just mention the Python code. Okay, but I think we'll cover four. But anyway, we just do two mainly. The main two thing is called the regression tree. Sometimes they call classification regression tree. It's called CAR. Later you will see it's basically you just do binary decision, splitting stuff. Okay, and later you will see what it is. It's very similar to the way we do the scatter plot, right? If you remember, I think we talked about this in topic 4. It's very similar to this bin scatter plot idea. You just divide your X into multiple sections and calculate average, okay, of Y, right? And the lowest is the same, but here this one only focus on 1X, right? And regression tree is basically generalize this to more than one dimension. Okay, but I'll become more. I'll get to more detail later, so don't worry about it. Okay. The other one is random forest. As you can imagine, forest and tree by name they're related. Okay, forest is basically coming from tree, right? Many tree become forest. Okay, so basically you would, something to ask, you will have many tree. Okay, and that will become a forest. And then you are trying to have some way to aggregate those trees, some average. Okay, so don't worry, I will become more precise later, but that would be the idea. Okay. So regression tree, as I have hinted, is actually similar to what we call non-parametric regression. It's actually same as what I said, right? The one that we have is the scatter bin plot or the lowest, right? And let's see the example, then you probably understand. Okay. So before we do it, there's some terminology. Okay. Probably don't need them all, but it's good to know the name. At least you know what we're talking about. Okay. And it's a tree. So it starts from somewhere. Tree actually means this type. I mean, the tree actually is not the tree outside, but it's a mathematical tree like this. This is called tree. Okay. Tree structure, something like this. Okay. And it's a binary tree. So it look like this. It start from the top and grow bottom. Of course, you can do like this. Okay, invert the tree. Okay, but I think most people would write it in the reverse direction, because I think people read from the top to the bottom. But you can also grow in this direction. Okay. This is called the top loop. Is in the top. Okay. Top loop. And terminal node is ending point, maybe somewhere here, depends on whether this end here. If end here, they're all terminal. Okay. And people would call all terminal point called the butt case. Just a name. I mean, I just put it there because I mean, very unfriendly. I don't know friendly or not, but machine learning use different terminology than econometrics or statistics. Okay. We use X is called independent variable, right? And in machine learning, it's called features. Okay. And Y is called dependent variable. Machine learning is called target. Okay. Anyway, but just a name. Here the free thing they call stopping rule. Stopping rule is saying that because you grow a tree, when you stop. Okay. And of course, by this, you have to decide this one of the hyperparameter you have to tune, right? You have to decide when to stop, grow your tree. Okay. The tree, you have to tell them when to stop. Okay. And branches is somewhat simple. We're just like, this is a tree, right? This is called the branches. Okay. Maybe they call edge if you like network idea, edge, but called branches. And cutoff point. Okay. Cutoff point will be how you decide whether you walk this or walk that. Okay. Later you will see it's like, as I said, right? You just cut the data left and right, go left and right, right? If the data is more than that, you go left, left and right. But you will see soon, okay? The cutoff point we will see, okay? And how you determine cutoff point is endogenously by algorithm. Later you will see clearly what do we mean. And this is what the size of tree here is. Look at how many split n plus 1. Because plus 1 is the first guy, so we just because last one you don't split, right? But anyway, you will see what do you mean by that, but more clear. But they are all only terminologies and nothing to learn, but just to know what they are. Okay, so don't worry about that. If you don't understand the terminology, we don't really mention it. We probably don't need it, but I just have to mention it because if you read the book or other people, when they say, then you have to know what they are talking about. All right, at least when you go to interview, right, you have to at least can throw out some terminology, right? Do you know anything about regression tree? Yeah, there's 3 terminal nodes, clubbing rule, level, size, whatever. You can just at least have to spill out something. Okay. Let's go ahead. Okay. So let's do this regression tree. Okay. And what I have here is we'll use a package called the Science Kit Learn, and we use tree. Okay. And the thing we use is called decision tree regressor. Okay. So that is exactly the one we use. So we very simple. For simplicity, I focus on one-dimensional X. So X only have one feature. The feature is 1, 2, 3, 4, 5. Okay. That is very easy. Okay. And the Y will be 2, 4, 5, 4, 5. Very simple. Right. And now, so what I'm going to do is very simple because everything is in back blocks for regression. So you remember from machine learning, just very simple. Just tell them what are your variables, and that's done, right? Of course, you tell them what model you're using, right? So just tell them X and Y, but before doing that, you have a hyperparameter to fit. Tell them how deep the tree you go. I just go one step. Okay, and later you will see what you mean by one step, but this is the one you control. Okay, you control by one step, and you just fit it. Okay, once you fit it, actually you're done here already. Okay, you're done already. Okay, and then you can test your prediction here. Okay, and you can print your prediction. Okay, and here is the regression tree. Okay, I try to make some sense out of it. Okay, so here what is doing in this model is you try to cut the data into 2 halves. I just one level in 2 halves. Okay, my data, remember I want to predict Y. Okay, so regression tree, what they're doing is to cut data into 2 halves. Okay, and then based on X value, and the prediction is based on X value is either 2 halves, is either lower X or higher X. Okay, and among high X, I have average of Y. Okay, and among, maybe I draw a picture, it's easy. Okay, what it's doing here is that the following X and Y. Okay, if I one level of regression tree is I forgot the number, maybe some number here. Okay, anyway, some data point. Okay, what I'm going to do, the computer actually do is the following. One level is I just cut X into 2 parts. Okay, and how to make this cut is the algorithm we talk about later, but the algorithm here, we cut it into 2 halves. Okay, and maybe I call this low X, right? And this low Y, high X, right? Okay, and then what we're going to do is looking at the average of this, I have a Y here, Y of the low. Okay, and I got here, maybe based on this data, I have Y high. Okay, and for this model to do prediction is if X is here, then it's my prediction. If X is here, it's my prediction. Okay, that's no different from what you learned from the scatter plot idea, right? That's very similar. But every time I just do two levels. Okay, you can imagine I can do more than two levels, right? I can cut here, then I cut here and cut here, so on and so forth, right? I can multiple two-way cut, right? I cut it here, and then I can cut and cut again, keep going. But this only one dimension X, but you can imagine I can do this multiple, but let's talk about that later. But this is the method, okay? And probably the next thing asked is how I choose this guy, right? The thing is, they will try to choose it such that to minimize the root mean square, okay? They run moving around this such that the error is to minimize, right? You get what I'm saying? So in this case, you can move the red one left and right, right? For each particular value of the vertical line, you have the root mean square, right? And then you can just pick the right one. Is that clear what it's doing? But one, I mean, of course, that's only one X is very simple, right? But at least we know how to do the simple thing first. And now you can try to see the example we have, why we are predicting this way. Okay, look at the data. It's simple data. 1, 2, 3, 4, 5, 2, 4, 5, 4, 5. Okay, and you can almost more seeing that below 1 and above 2 is a two different world, right? 1 is back to 2, and basically 2, 3, 4, 5 actually map to a much higher number. So basically, X is below or less, around 1 is a low X low, right? And the rest is high. That's how you do it. So that's why you can see how they do it. Okay, that's how I do it, right? When X is less than 1.5, go to the left-hand side. More than that, go to the right-hand side, right? The prediction is 2 here. The prediction is 4.5. Why 4.5? Average, right? You can 4, 5, 4, 5, right? So average 4.5. Is that clear how you get this one? I mean, this is simple enough. I think you can actually check it. But of course, it can be more complicated, right? Because I only allow one level, right? If the data is a lot, many level, then it's not easy, right? Because you just do the tree many times, right? So let me finish this example, just 2 slides, and then we have a break, okay? More quickly, okay? So in this one, they use the used car data to do prediction, okay? And they look at the data from looking at Toyota car in 2018 in LA and Chicago, 477 data, observation, and they just make it simple, okay? And how to do training? They just do the simple training test split, just do it one cut and do prediction, okay? So N is 333, okay? So they do one cut, what they show it is, okay, whether the car is 8 years old or not can be different, okay? 8 years old, okay? Less than 8, more than 8 years old, the average price, no, I think it's average price. Yeah, average price is 4,000. Less than 8 years old, the price is 11,000. Before that, the total average is 5,000. Okay, and this how look at the graph, right? They cut in here, 8 to cut in this way. Okay, and as I said, how they pick this particular line is to they keep moving until the mean square error is the smallest. Is that clear? Okay, of course, after the break, I'll talk about more than one X, then will be more fun, right? But at the moment, I think we should have a break here. Okay, we'll talk about those. Okay. So you can take a break. If you want, you can do quiz. I mean, but it's a break now. Okay, it's a break now. Quiz is not start until 2:30, but you can do it earlier. There's no difference. I don't eat lunch, so that's why. 做唔健康又會就好意思講。教唔食嘢，又飲唔飲，講到你好健康，做唔健康。呢個唔掂。你睇下嗰個標籤。我也是。OK 咯。每日都咁有。哦，沒有，上課我才喝。這樣子，要有咖啡呢個，然後就我哋咖啡嘅就蚊罐，係廿蚊收。有啊，我有呢啲，我之前有呢啲。咁買話700塊。打算公嘅啫，我喺3號嚟廿，打3蚊11。健康都冇辦法㗎啦，係教因為你教書嚟講我都好啊嘛，一定要嗰個冇講啊，我諗唔講咁多嘢嘅。我教咗3年嘅手術，說我現在教3分多，這個應該地方應該。我也買了這個。而且可以拿起來，沒有拿。錢10塊錢，883片都得買都。可以的，下回再问。下次你给他吧。下次我加了。那个这毛跟水。竹蔗毛巾。好。啊？對，好。加好了。要喝那吗？应该都会吃有点因为他们啊，我只因为每种调食就是比较热爱。我们都在楼上嘛，对，拿一个啥呀？我要不打比较点，也不是拿的。还挺说，但是有，我觉得下，当然，你这个必须怎么改？一般不会喝这么一般最多5个。基本上是书吧，我每天烧菜我。没想到，你们这边我刚才比我超越很快，更好，可以吃一下饮料的，非常好，非常好。这个什么过了？但是上个课跑步了，好像刚刚自己啊。我每次回到深圳，今天就要今天奶茶了。今天的，今天去。对。我刚才说的，你要在那出吗？
我也打算换一个，都不是好几年。
不远。他现在不是很便宜吗？在深圳。
是吗？至少比香港贵。
我这个是在中国大陆配的，
在哪里？
在国师银行。
哦，那他们国师。
打的我也用，没用。什么？没办法，我有钱的话都想配个好的，挺好。
因为我分手，我恐没跟这样，同一不行。
太薄了，太薄了，我都可以。我是怕你搞，这不要黑吃饭，来过，我有钱的。我在諗做嗰啲私募股㗎。啊，好嘢，股票，我哋有個嗰個咪嗰個就係保險，嗰個就保險，嗰個攞嚟呃價紙喎。係啊，嗰個就保險，冇㗎啦，冇。以前我新加坡就可以，我哋新加坡係都大。
你應該交同你嘅代大學。
我哋公司長大，大人就。啊，你说后面部的呢？已经交了。
他是我们后续就是我们要带动。
他可以再带。我们今天那个不用吧？
我就是问这个，
我一个不用嘛。啊，你可以加不加进去？
因为我看那个你在 project 跟东西，所以我问一下，我们这是对就是尽早的出，然后描述。
那描述一下怎么样？看简单。
那我们需要说，比如说我们的要提供，比如说，我大概就是那个大。
不能对，很简单。这个不需要，我没有 appendix， 我需要 appendix。
不需要。
我没有 appendix， 你可以加，但是我不会，I'm not going to read more than 2。
具体哪个关口看一下。大学应该7倍，然后
啊？那个医生我因为我把当做刚才说的港大他们的。
哇！都港大一般。
今天有后天，因为我是华人。
怎么不去？
这个啊，因为我都照着你做的，其他都挺少，基本上香港的学校老师差不多。
挺高的是吧？
对。
看老师，你看官网的上面这个去哪里？
这个教程不行。
你有看过吗？
没有看过，他的翻译，他把我。
你翻错，
他就随便批的，我都不管。他在跟我说的胶片啊，新加坡、香港。打一个的电码，现在跟现在因为很多上海的好，这样现在不管。 现在那我觉得在香港，那这个过来啊，对，我发过来，
等于我上 ABS 了，等于我上 ABS。
香港有不符合整个生活水平的就去晚一点，兴趣我做了差不多10年，做不了。每天都演，但佢嗰啲係濕嘅地，太重。現在另外，這個部分你知道我一般很多同學剛走過來，我已經馬上就給他，如果我要是等於一條街都冇。外面就不了，沒辦法。所以為什麼不吃飯呢？我都懶得出去吃飯。鼓勵這個地方啥都沒有，封閉片成一樣的 size。
他在那个还在外面呢。
之外。
那还有家庭
只有這個最大的東西，南洋在這裡，南洋就是馬來西亞。哦，對，大概是這樣。你又畫錯，你唔好畫錯添，畫咗落去。呢個數畫咗，這個新加坡，周假你有搞嗎？還有這個。CBD 的，也有這個，在裝搞那個SMU 的，有 NUS 的 SMU 是什麼 ？SMU 是什麼？新加坡管理，新加坡管理新大，新加坡 Managerial。
你在哪？你在
NUS 没有，只有聽說。哇！對啊。
单峰，
你们上班是做开车还是坐车？
我都是租车的。因為錢啊，而家嗰陣時我都4000幾，好喺入邊住。靚啊！我邊度都有搞，哇！靚嘢，新加坡都，仲要按你香新加坡位置，攞安度啦，咩安度，它所有這個私宅，它有幾個私宅嘛，都私宅都有，這個它不一樣，變太多了，沒有東西的話就沒有。現在非常多。你看這個地方，
這句話，
裡面都是填的，全部填出來。有幾遍填的，有幾個島都是填出來。所以它本來從500平方公里，現在變成700-800，這樣子一片。在香港的話，山太多了，基本上用多少？所以正好填，你到一個機場都填出來了，香港都填了，這個啟德區就是啟德區有填的，對吧？我們本來對面馬鞍山也填出來，以前沒有打過的。西角有個地方也是出來的，它從別的地方都是填出來，很漂亮的地方都填出來。很不好意思，可以看到我們香港應該有幾個山的。如果有什麼平的重大的那個簡歷就在那對面了。你們想到出來一個都是哪邊沒有山？
下回早上山雞。
Anyway，你們可以做下 quiz， 有時間的。
沒有時間。
Time to do the quiz. Okay, I think they try to do that. We do the quiz a little bit. 啊？
是5分以上嗎？
很少吧，这期只有 only eight question。4分或以上吧。4 or above. 4 or more。 Oh man, more than 4 is fine. More than 4. More than or equal to 4. 没事啦，如果大家考不好，来找我，给你一点小任务就可以。帮你收的。啊，不是，给你给你再做一下 inside。
做 exercise。
可以给我的表再投。我有我做的。哦。对。刚刚火线。怎么打5个了？得罪了。可以在干嘛？我工作都在玩，先好就过来，说到现在，多长时间了？没所谓吧，3个。哦 ，OK。也不太稳。好像这一题，seems like there's some problem with this part. So as long as you get 3 more, then you can do that. The problem with the platform. Anyway, I don't know why the blackboard like this. Anyway, not my problem. OK， 我睇當啱啦，啱3題啦。 station 好，我到，不到，不好，不到。Hello，Hello，Hello，OK，你好，你好。你好。哦，对不起，对不起，对不起，一个。interaction 对的，没错。Jadi kamu cakap tinggi kau begitu, ini betul cakap ya. 機會係。我就想做啦。自己 export 我有望過嚟。因為我今日不得最多公寓應該係你識咗去重做，識咗重做。10 more minutes, 10 more minutes, 10 more minutes. Easy可以解决，还是你还可以用什么？都可以做，就是这个两个，如果是你看了这个会用几年？因为我好像现在对那个现在我们是可以的，这就是那这个那些我好像是加一套什么的，其实可能基本上如果是旁边这个比较可以。或者我无忧好因為做緊啦，基本做緊一個身吹嘅嘢就，我就睇到好似之前收台灣時班， 我都打在我在美国等等我都打过我可能会现在领跟不打嘛，我就讲这场我觉得很长，我也觉得有一个非常有一个在一个人没有力来的。跨度很大，基本上把我说鸡蛋都打出来，科基本上是一个涵盖的面积，基本上是说的很大的那个。他们只要个体高把为什么几乎把大哥怎么？姐怎么样？刘姐姐怎么样？对，但是小的，对啊，然后你听的这为什么点？
贝塔加上一个快什么的，对，
所以就不会这么简单，取决于谁。
所以他如果比较的话，那他是
一般节多一本必须啊，对啊。
在那个空有，就是我们是有那个零是那是一样。那如果又这里有在做，
有问的吗？什么问题？原来的问题。
就是在没有我们它这个系统都是对所有人的，不是对所有人的。
对。Last 2 minutes, then we start the class. Please. 一个大神，哇，就做一个厉害，真的大神啊，真的大神。真成8了，但是应该是没问题的，大概就是便宜价，便宜价，有少点，大三就没有多少的，大家看没有达到我对大家觉得很容易的感觉。太容易口出。
So I guess I should start. Please submit. It's done. So don't worry. I mean, as long as you get more than 3, then you get full credit. Okay, 3, 4, 5, 6, 7, 8, then you got full credit. Okay. Now I guess we should continue. Okay. So here we have a 2 levels of the tree, right? And we have 1 cut, right? And some of you actually ask, how do you do more level? Because I have maximum depth is 1 here. So let's see how we can do that more. But okay. But the question probably, as I said, how you would cut is you pick a number and then try to do every single thing. Okay. So now here is the problem. Remember the car problem, right? So they cut it into above egg and below egg. Okay. After that, right, the data cut into 2 halves, right? And these 2 halves can cut again further. Okay. So every time I do bisection. Okay. So between 1 and 7, you do another cut. Above egg, you do another cut. Okay. So so that is what they get. Okay. You can see this one is actually looks pretty nice because originally you have 5,000, right? And once you cut into half, it's 3,000 and 11,000 and further cut, right? And actually, it does suggest the age is very useful because given the age, right? And that's what you get, right? So remember, this the last one is the model, the last part, right? So this graph is already the model, okay? Because what is the prediction? Is you give me the age, okay, of the car. What's my prediction of the price? How you do? Suppose you give me the age is like, I don't know, 10, okay, 10, say 10. How I go? First one, I let yes or no, yes, right? And here, yes or no, no. Oh, well, no is here, right? So, yeah. So that is how you do, right? And if age is 2, then you just go this way and this way, right? So that is how you proceed, right? So you end up with all the bucket, right? Here, this is the prediction, right? But you all have to go through one way or the go through step by step here. Is that clear? I mean, it's non-linear, right? Because it's not there's some discontinuous jump, right? Because suppose you have 8 or 7, right? The model can be very different, right? Because suppose you have 7, right? 7 end up like no, 7 end up here, right? 8 or 7 is here, right? And if you're 9, then you're here, right? So there's some discrete jump over there. It's not linear, right? And you have 8 or 9 is actually here, right? So it's non-linear, right? So, and some of you during the break asked me if you want to do non-parametric method, right? The lowest and this card I would recommend you do this one, right? Because this is that one is smooth, but this one is for prediction purposes better, right? But the lowest, that one is better for explaining the model, right? Because continuous is easy to see, to fit, but if you do prediction, this is better. So I think it's a different purpose, right? Depend on what you're looking at. This is machine learning is good for prediction, right? It's not good for explaining because there's no, that doesn't say anything age, right? 8 or 9 will give you the same answer. Sorry, 9 or 7 gives the same answer, right? Or 5, actually 5, I mean 0, 1, 2, 3, 4, 5, the same answer anyway, right? So it's not really good in terms of explaining, but it's good for prediction, right? If you want to minimize the, say, root mean square error, that's the best, that's the model you're using. Okay. So here is just what I said, the stopping rule, but I guess already talked about that already. So I just don't go into detail. Okay. So this is the graph, okay? And in fact, it becomes a step function, you can see, right? It's very similar to what the scatter diagram is, just like divided into multiple parts, and this that is the model. Okay. Now, and this output, right? But that one is just basically output the diagram of this one, right? The tree become this guy. So there's nothing new there, but it's a way that you show it. Okay. And you can see here we have actually 3 levels. It's not symmetric, right? Because the program will decide whether they further cut or not. That is called the, remember the one is that is the maximum. Okay. And it's not saying you have to go that far. Okay. And there's some algorithm to decide. Do we discuss? There's some way you can tune the parameter to decide how fast you can go. Okay, but we're not talking about those. We just left it the computer to tell us. You just tell the maximum level you want to go. Okay, and the computer will decide. Here I just have one more. Okay, and whether you go one more actually is looking at the root mean square error and look at complexity of model. There's a punishment. There's some way to fit it. I think it's way beyond our class to talk about those, but we just left for the Python to do it for us. Okay, for our purpose. Okay, so okay, you have question. So that is, you cut in this way. Okay, remember it can be asymmetric. Okay, if you fit linear, that will be something like that, right? If you fit a curve, it looks like that one. Okay, and of course, you can look at the model. Okay, you can see if you run the regression, linear regression, linear fit, the error is large, 2004. But if you even fit the tree, right, need not be better. Okay, even though more flexible. But if you have 5 terminal nodes, actually it's much lower. Okay, in that case, you probably would pick either these two, doesn't really matter. And the choice would probably, it's not clear which one you would pick, right? Because this is less complex than this one, right? But of course, if you just want to minimize the root mean square, then this is the one you pick, right? But to me, it's not entirely clear which, because so close, it's not clear because sometimes you want a less complex model, right? But at least you don't use the linear one, right? For sure, it's the error is so large. Okay, and this M1 is too simple. Just left and right is not good enough, right? The reason is non-linear, right? So it's not good. And now we generalize this to multiple predictor, right? So so far we just have H, right? But what happened if you other stuff? How can we do that? Okay, the same idea, right? And you can see that many trees. You can see how they do it is the first round, they look at many variables, right? Each variable, they will just move around the cut and cut it into half and choose the variable and the cut off that minimize the root mean square error. Okay, and you cut the data into 2 halves, right? And same for the rest. Is that clear how it's being done? Okay, just imagine 3-dimensional x, x1, x2, and y here, right? So the first cut is you may cut in x, this dimension, or I can cut this dimension, right? Regardless of what you choose, a knife and cut it in 2 halves. Once you cut it this half, you decide to cut here further or cut here further, right? For this half, you decide to cut this or cut this. Okay, so the cut can be different, right? This use H, this use odometer, and so on and so forth. Is that clear what is being done? Okay. Maybe do I need to draw something like that, right? It's a okay. Suppose the data I don't draw 2 dimension, but x1, x2. Okay. And suppose you would cut first, you have to think about whether data is cut in this way or data cut in this way, right? You can just go up and down, go left and right, pick the best cut, then cut in 2 halves, right? And suppose you cut the data you cut is cut in this one and this one, right? We call left and right, suppose, right? And once you do this, you will decide whether separately, decide whether you cut in this one or you cut in this one, right? Or you can cut here and cut here, can be different, right? So then you keep cutting until you're done, right? So you can, at the end, you can cut in the very complicated, okay? That is, the computer will decide how to cut. So that is the machine learning, how it's being done here, right? Is the computer will decide how the model proceed, okay? As long as you give them the criteria, right? When to do the cut, when you don't further cut, so on and so forth, okay? But I mean, yeah, in the Python already, don't worry, already built in the package already, default the value will be good enough, okay? Usually, I mean, unless you are super crazy, usually you just take the default value will be fine, okay? You don't need to worry about that much. Usually don't worry, but of course, as I said, you can tune the parameter if you want, but usually you don't really worry too much about that. You just decide how deep you want. And as far as I see application, usually people don't go more than 2 or 3 steps. I mean, in terms of the depth, maybe 3 or 4, maybe at most. I mean, 5 is very rare. Maybe 5 is the maximum I saw when people apply in practice. Unless you have a lot of regression, a lot of data. Of course, how deep you go depends on how big your model is, but in general, I don't see people more than 5. Okay, when you apply this. Is that clear? Okay. This is a tree. You go to the tree, and then that's how you do regression. It's like kind of regression, right? But just cut. Okay. But anyway, if you talk about 2 dimension, right? At the end, what you get is you basically cut things into very small pieces, right? Something like that. At the end, maybe something like this happening, right? And the predictor is just basically this one average of y, right? This find average for each small pieces, right? The prediction is if you're here, right? The data is here is just an average of this, right? So that is at the end, it's like you cut this into very small squares, or rectangles, and just average of this value, right? Is the prediction. So it's nothing very deep, right? But how to cut, right? Is binary. Every time you cut left or right, up or down, right? This is the cut. Is that clear? Okay, I hope. At least, I mean, the method is very easy, right? You read the book, but I try to give you the idea what is behind, right? Because you can just, the Python is very easy, just done, then you're done, right? Just very fast. But probably you want to know what is going on there, right? So, then probably I have to mention is what we call, when you do the split and not do the split, okay? It's called the complexity parameter, okay? which the parameter you can tune, okay, is asking with the split actually reduce the root mean square error by how much you allow the cut. So it's a threshold of the cut, okay? If you improve by this, then you cut, okay? So this part, I don't think you would worry about this part because I think, do I mention that? I didn't have that, but usually you don't worry about that. I think it's, yeah, you don't need to worry about it. Just you take the default value we find for our purpose. And you can change it by the Python, but usually we don't. Usually I see people, no one actually touch it. Even the people do research, they don't really touch it because usually default value will be work very well. Okay. Is that okay up to here? It's nothing very deep, right? Depends on, you can tune this parameter, but usually we don't, right, as I said. The main thing you control is the depth, usually, right? How complex a parameter you want. Okay. What is the problem of this regression tree? I mean, of course, it's very simple, right? And one problem is overfitting, okay? Because of the way you do so many cuts, okay? And of course, you want a higher CP, right? Which we want to do the cut if they actually improve the model. The one way to do it. And the other way to do it is the splitting is not robust in the sense that if you have some data add or subtract, actually you don't get the same result. Because for normal regression, you add and subtract, usually the slope is not changing. It's because the data changes continuously, right? But if you can see if, say, suppose I have where am I? If you do the tree, right? Suppose a 2-dimensional XY, right? There's some dot here. Okay. If you cut here, suppose you cut here, right? Your data is here, 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 right? Suppose the data goes to the right-hand side, okay? Then the cut will be different, right? Some slice in the model, or then the cut is not really robust, okay? So the one way to do is they call the pruning, okay? But I don't go to detail, but you just have the tree and cut it off and grow again, okay? But I'm not going to talk about that. But there's certain way to improve it, but I think it's way beyond our class to talk about those because, as I said, right, you have to study a whole semester to do machine learning, right? I think you do in second semester you want to do machine learning. I think it's part of your course. It's an elective if you want to do. So if you want, you can go there. So it's not my job to go into very detail on this, okay? But you can see as like this, okay? Who can read this? I mean, no one can really understand what's going on there, all right? So usually you would, this complicated, okay? You would cut the tree, okay? Just pruning, just cut it, okay? You grow the tree and cut and go again, okay? Until you get the thing that you need to do, okay? And the next thing is what we call, I don't have put it there. Is what we call a graph we call variable importance, okay? That is because the tree can be very complicated, okay? It's very hard to read, okay? So the idea is looking at if I have a tree, okay, and I have this variable, okay, I can explain this much. Now I take out this variable, I have the model, okay, and if without this I explain much less, okay, then there's a contribution of that, right? It's how important is this variable, okay? So the ideas look like this, right? And you try to check, okay, what is importance of this model. Of course, the higher the better. Okay, I'm not going into detail of how you compute this guy, because too complicated, right? But anyway, this is in some sense you can imagine this coefficient of regression, right? This is very important, and this less important, and less so on. Okay, so the odometer is the most important, right? Is I think it's looking at how far the car has been going, right? And age is also important because they are how the car being used, right? And the other, who is a dealer, right? Or other thing will also be important, but less important, right? The two is most important. Okay, so it gives some idea that you'll be there, and you expect naturally if you run regression, this will be consistent, like in this style. Okay, relative sense, right? You expect the coefficient for this one will be higher than this one, and so on and so forth, right? Is that clear? So this is the graph we try to look at. Do I have put? Oh, I didn't put that. I mean, maybe I should check this. But you can easily produce that by the Python code. Maybe. Anyway, I should be there, but I don't know. Okay, I'll check out. I mean, I put that back the Python code in the slide. But it's easy to produce. It just ask a package to produce this is easy. Maybe I should add that back to the slide. Okay. So that is the idea. Regression tree is a non-parametric regression. Okay. So here we give the why we want to use it, what is a good or bad. Okay. The happy first one is very simple. You just don't need to worry about the model. Okay, just put all the variable there. And the way they build the model is called the top-down approach. Okay, you start with a simple model, right? And you go down. Regression is really different, right? Regression or LISO is different. Right? Regression is that you have a full model, right? And the regressor tell you which is gone, right? Here is you start with a smaller one and build up. Okay. Right? Opposite of LISO. And this pattern means that you don't need to worry about nonlinearity, right? Whether quadratic or nonlinear is taken care of. Right? Remember the case of H, right? It's nonlinear, it's a curve, but it's taken well by this tree, right? Because remember, tree is better than linear, also better than the quadratic version. Okay. And actually, this statement is actually a mathematical statement. Okay. It's saying that regardless of what kind of model you have in the regression, okay, this can accommodate. Say, suppose the underlying model is like this. This regression tree will able to approximate that, no problem. So suppose your model is like alpha beta x1, beta 2x2, and beta 3x1 square, beta 3x2 square, beta 4, beta 5 x1 x2, and can be more. Okay, and you don't need to specify it. Just run this, you're done. You don't need to worry about how they interact. Okay. And of course, the two things, as I mentioned, is extreme value and it's not very robust. Okay, because depending on data, if move around, the model will just very different. It's not very robust. And also the bad thing is black box, right? It's very simple. I just click it and you come out, but you actually don't know what actually it's doing, right? Of course, you know it's minimizing the prediction error, but it's non-linear. So actually what is minimizing what you're looking at is different, right? It's different, right? Because regression is very simple, right? It's a minimize the vertical distance. It's very clear, right? But this one is, what is minimizing is not entirely clear, right? It's not entirely clear what you're minimizing, right? It's not saying that you try to build a model, right? It's not, you're not doing this, right? You're not, remember, you are not, you may tend to think, okay, you attempt to think we are minimizing this guy, right? This is not, right? Because once I move this around, the mean actually changes, right? So depend on how you draw this, right? Then you're minimizing different criteria. So the criteria to minimize is not really clear. Of course, you given the cutoff, I know what's minimizing, right? But this cutoff is endogenous, right? So it's not entirely clear what you're doing. Okay, so that's why black box model, although it's good, but you're not clear what you're doing. I mean, although you, in principle, you know what's the algorithm, but it's hard to interpret what it's doing, right? Suppose I add another data point, the whole thing would change, and then, yeah, what are you doing, right? I mean, you tell your boss this is my model, and next month you tell your boss this is another model, okay? Another day another model, so probably it's a kind of weird. But anyway, it works. That is what it is. Okay. So I hope this is clear. So finally, this is a comparison. I think it's good to go over. Okay, because I think that is how especially you do your project, and this is you do prediction. That is something that you want to know. Okay. And OS is a formula there, right? Because it's your solution is like, right, the covariance over variance, or there's some method, right? And the regression tree is actually there's no formula, right? How you get this coefficient is no. There's no way to actually get the coefficient directly, and they all minimize loss, right? MSE, and how you solve the solution is minimize the vertical distance for OLS, and regression tree is what we call greedy algorithm, which means that every step we do step by step, right? First step, first cut is minimizing the immediate MSE, right? And the second one is also minimizing each part, right? We are not optimizing over the overall MSE, right? Because each step I just minimize the MSE in that part, right? Each cut I do it like immediate minimization. So that's called the greedy algorithm, right? Just we do it one step without thinking about the future, right? Just thinking about immediate happiness without thinking about the overall happiness, right? So that's what you mean, okay? And variable selection, right? X is predefined, and car has no defined because you would take, right? And the result of regression is bunch of regressor, and the regression tree is actually bunch of terminal nodes, and the tree according how you go there, right? And the predict value, okay? And regression is different X and different Y, right? But the tree is like you cut it into multiple rectangle, right? So within the same rectangle, the same value, okay? And here is a linear relationship, okay? And for the tree is you try to approximate any non-linearity, okay? So it means if your data or your regression you think is linear or it looks linear, so don't use the regression tree, okay? Just don't use it because you can, okay? Because to show off, you know it, right? Choose the right tool, okay? Just because you have a car, right? You don't have to drive. You have to, sometimes you walk, sometimes take a bike, right? Sometimes choose a fit one. And for nonlinear, okay, for regression, you need to know how they nonlinear in order to regress. Otherwise, you'd get a wrong model. But for the car, you don't have to worry about that part, okay? Even nonlinear, you take care of by itself, okay? So that is the regression tree problem, okay? So here is a overall comparison, okay? You have different models, okay? And different MSE, okay? And you can see how they run it, right? Different levels, different complexity, whether the tree is being cut, pruned or not, and then linear or multi-norm, monotone, okay? And you can see, okay, surprisingly, probably a little bit surprising, this one actually performed very well, ORS, okay? So it's unclear whether you want to do a complicated model, right? In that case, OS is already do with interaction term, polynomial term actually do very well. Okay, so just to a gentle reminder, right? That is sometimes it's better. If the thing is linear, right, then actually help. Actually, regression actually better. Because remember why a tree may not work very well is because it's not continuous, right? Because in the same rectangle, you predict the same thing. But you can imagine in this car case, right? The H and odometer is actually continuous, right? Right? Then that one is not very well captured by the tree. Okay. I suspect that's the main reason why it doesn't perform very well, because it's not continuous in the age. Okay. So after the break, we talk about random forest. Don't worry, we're not going, it will be just a very simple extension of the tree. So shouldn't be a big thing. Okay. So let's have a 15 minutes break and then we come back for this random forest. So I think I have to continue. Okay. What is doing is random forest. So don't worry, it's not something complicated. Okay. Conceptually, it's a little bit more tricky and a lot of details. But as I said, our class is applied, so not going to be bothered with technical details. In case you want to know more details, there will be a whole course, machine learning, in your second semester. You can have fun. Okay. I think this is the last machine learning that we are doing, right? I think next class is no longer machine learning. Okay. So this is we just do it one single class plus LISO, half class for machine learning. So if you want to know more, you can read a book or you can try to do the data cam, right? There's a lot of machine learning there. You can have fun. So let's do the more fun machine learning, random forest. Okay. And what are we doing is called the ensemble method. Okay. It's trying to combine different methods together. Okay. It's just like the use one method is not good enough. We use multiple methods together. Okay. So it's just combining different methods together. Okay. So that is why the forest is multiple tree. Okay, combined together. And random, you will understand why we call random, but there is a forest method. Okay. So let's go step by step. First is regression tree turn out to be a problem because it's overfit. Okay. Even though you try to do a lot of stuff, it doesn't work very well. Okay? Because still a big tree. Okay. And overfitting is an issue because it really depends on how you do the thing. And how do we solve this problem? Is what we do is we have grown many trees, okay, and we combine them together, okay. And if you look at the book, they call the wisdom of the crowds. It's combinable, right? It's three stupid people is smarter than smartest people, right? 三个的臭皮匠胜过诸葛亮 something like that. Okay. 三个诸葛亮 Okay. So that's actually 三个诸葛亮 Anyway, so it's combining, and there are actually two different ways to do it. Okay. It's called backing and boosting. I think we just do the one of the thing, but let's talk about that. The first one is called backing. It's called bootstrap aggregation. How do we do it? Is we actually create not the data set we have, is bootstrapping. So we create k different data set, right? Remember, bootstrapping is you have single data set, right? You just keep drawing the data and you create another data set, right? Just we artificially create a data set. Okay, let's bootstrap it first. Okay, and what we do is each data set we have a tree. Okay, and somehow, I mean, we don't talk about somehow, but somehow there's a way to aggregate it. Okay, we don't even go further. I mean, the book didn't go further, so I don't want to go further, right? But you can check if you want, but that's how they do it. So very simple, right? You bootstrapping, right? You just like the data, you bootstrap it, right? Produce many data. Each data set, you have a tree. Somehow air phrase those three. Okay, we don't tell you how, but suppose we know how to do it. The other way is called boosting. We talk about that. This is a random forest. This is called the greatest gradient boosting. But anyway, we talk about that. We'll mention the Python code. The way again is also bootstrap. Okay, but the way you go the tree is not averaging. Okay, independently, you would first build a tree first. Okay, use a model, of course. You build a tree and you cut the tree somehow, prune it, and based on this tree, you look at the second data set and refine the tree and keep refining the tree. So it's only one tree you keep refining. It's not a different tree there. Okay, let me draw a diagram, maybe easier. Okay. The first method is the following. So regardless of what your one data set, right? Data set. Okay. And then you do bootstrap method. You have K different one, right? You have K different data set, right? And bagging is asking you to go a tree here. You go a tree, right? It must be a different tree because depend on how you because randomization, right? Because bootstrapping, right? So each tree be different, okay? And there's some way to average those rules, okay? That's called bagging. Actually, this is called a random forest somehow. I mean, and the later one we talk about is instead of doing this separately and average out, you will have this tree here, okay, and bring this tree to here, okay, and do some way to improve it, okay, and again go next and go next, okay. You carry a tree, one by one, okay. There's some way to modify it. We're not going to mention. Even the book didn't bother mention the detail, so I'm not going to bother you with that. If you want, that will be you study in the second semester, okay. Not my problem then. You will bother with that, but that is the main idea, okay. I'll talk about random forest first, okay. There's a random forest, right? One way to do bagging, right? Remember, we go tree one by one, okay? And there's no pruning, so don't cut it, okay? And what is the random forest here? What's the random here means? The random is this one, okay? Is because if you still build a tree by bootstrapping, okay? And you may build actually the tree is very similar, right? And then actually you don't solve the overfitting problem, okay? Because then how the randomize is you randomize on the parameter M, okay? Each time you go to tree, you only use particular M variable, okay? So what it means is the data is here, right? Maybe I draw it again, right? So what I do is I have a original data set, okay? And I actually create multiple one, right? That is called the bootstrapping, okay? And I randomly cut out some data set. So I cut out this part for this tree. For this part, I cut out this one. And for this part, I cut out this one. Okay. Then I go tree for each data set, average out. And in that case, tree are not so correlated because, say, for example, in this one, I use age for a car. And for this one, I just use color or dealer of the car, and here I use another variable. I randomly cut out certain stuff. Okay, that is how the random forest, the random here. Okay, is that clear? So basically, random use a part of the data only. Is that okay? I'm not going into detail because the book is not in detail, so I don't bother, as I said. Okay. And that is the random selection that make each tree uncorrelated, right? Otherwise, if you still use all variable, actually these three are so similar, combining them actually no use, okay? And you can't solve the overfitting problem because overfitting is what is you use the feature too much, right? By cutting out some of the data variable, right? So you just try to make sure that some of the specific pattern that is shouldn't take into account is not there, right? That's how they do it, okay? I think that will be sufficient for our purpose. As I said, if you want to know more, I think even the textbook don't give you more than what I said. Maybe slightly more, but not too much more. And if you really want to go further, you have to study another class, okay? And the question probably would be, what is number of tree you do? Rule of thumb is 500. Actually, this one you have to input in Python, okay? 500. And how many variable you want to do it, usually it's the square root of random variable. And then how to make the size, usually 5, 10, or 20. So make some small trees and combine them. Okay. And that is how you do. Okay. You will see. Okay, I go step by step because it's a little bit tricky. Okay. As I said, this is the ensemble method, so you would load the ensemble library, and we use the random forest regressor. And for this one, I think you have seen it before. This is nothing new, but just create data set. So you don't need that for your own data, okay? Because it's great data. And oh, where's my color? So for this line, this is, I think you have seen this before. This is trying to divide the data into two parts, right? Validation approach, training and testing, okay? And the randomize the cut, okay? You will see is going to be this one, this line, that you see it. And the last one is very simple. Just you need the mean square error, just load it, okay? So that's why we need this 4 line. And the first line, I guess we have seen that before, is we have the seed 42, okay? This seed is going to make sure that even is random forest, you always get the same answer. It's not random because you're IT manager, right? You know how random number is being generated, right? There is a random table. It's a deterministic random table, but you just go over the table, right? And the randomness comes from the starting point where you start, right? But where you start actually comes from the computer clock, right? Because computer clock is kind of random, but depending on when you press a button, right? So that is how the randomness comes in. But when you have seed 42, just you start from the starting point the same, so you always get the same answer. So that is why we always do this when we run it, and you don't have to use it when you actually run your regression. Okay, but I just put it there, so make sure that if you run, you'll get the same answer as I do. The second line, as I said, is a data, artificial data. You have a sample of 100, feature is 4, right? Remember, feature is number X. Okay, noise is 10. 10 is just make sure that how large is the variance of the X, and random state is the C, right? And this one is try to cut the data into 20% to 80%, right? 80% data you want to train, 20% is the one that is going to be remain there, and use random seed because randomly pick up the data, right? Because it's not going to be first 80 and last 20%, right? Just close your eye, you draw 20%, right? Or draw 80%, doesn't matter. So to build a model, you see the model is super easy, right? Just call random forest regressor, then you're done, right? And then you tell them how many estimator you're using, right? And the depth, how deep you're going, and you feed your model based on training data. You test your thing prediction based on that. You calculate the mean square error based on your result. Square is false because I use the root mean square. If I have true, then with the mean square error. But they're the same anyway because the square doesn't really matter anyway, as long as it's consistent. And then you can print that out. This is how we do random forest. And as we know, random forest is combining different tree, right? So there's no way you can represent this in a graph, right? Because it actually means that there will be 100 tree, right? Number estimated, right? The 100 tree, and there's no way you can draw 100 tree and you can understand what's going on, right? So that's why, although you can easily do the prediction, right? This is the model, right? It's hidden in the black box, right? As long as you give me what is the X, I give you the Y, right? Is that clear? So the model is hidden. You can't really see what's going on. But how should we understand this? There is one thing, as I said, is called the variable importance. Okay, I mean, you can do this for the, okay, that's fine. You can do this for the regression tree, the same thing, okay? I use the panda, that is just to get the data, right? And then I use the PY plot, two-dimensional plot, okay? What I do is very simple. So I just declare panda series, okay? Just the number, right? It's random forest. This is feature importance. Very rare, you have underscore at the end. I don't know why, but just the way they call it. Okay, this is just is a bunch of number. Okay, and depending on the index is based on shape. Okay, and you sort them. Okay, because it doesn't sort, so it's just sort from largest to smallest. That's a standard way people do it. Okay, and you just try to draw it. Okay, so this is the model you can see. I don't put the name, but you will see feature 0 is very important. Feature 2 and feature 3, and feature 1 is useless. Okay, and do remember, you actually run a lot of tree. Okay, and you're actually averaging out many tree results, and it tells you in most of the tree. Okay, 0 is used for the purpose to explain, right? And 2 and 3, so on and so forth. So if you run regression, you should expect something similar as well. Is that clear what it's doing here? Let me repeat it a little bit because it's a little bit tricky. Okay. This one, okay, is no different from when we do the regression tree, right? Regression tree also has something like that as well, right? But regression tree is very simple, right? Because you can see I take out this variable and how it helps, right? And then you can do the same for this one, right? You take out this feature 0, okay? The feature 0 is basically very important, explain most of the stuff, okay? And 2 and 3 is not very important, but you cannot say too much about how 0 changes lead to what. Is it monotone, right? Says feature 0 is going to increase 1. Is it go how is it going to increase? Change? I can't tell. Of course, you can fit in the data, okay, and see what happened, right? So for example, you can fit in the model, right? You can fit, say, feature 0, feature 1, feature 2, feature 3, right? You can try 1, 2, 3, 4, and you can try 2, 2, 3, 4, and see how it looks like. But it's non-linear. So testing this is usually not very useful. Okay, you can't say like a regression, right? This one you can check out what's going on, but here you can't really check out. You can't say feature 0, I increase 1, decrease 1. What do we get? We don't know. Okay, we can still write something, but you can't say globally or even locally. You can't say, right? Because it's tree, right? It's averaging tree, right? Is it going to make a difference? Probably not. Maybe if the tree, all the tree there, they group them together, maybe there's no change at all. So even though it's very important, maybe some slight changes has no impact on the prediction. Okay. So it's very difficult to interpret what do you mean by random forest, right? For the tree, you still have something to say, right? You can still trace the tree. If you draw the tree big enough, then you can still know what's going on. But this one, if it's not changing, what does that mean, right? Maybe or changing, what does it mean? Is it because of the tree, the second tree changes, right? You 100 trees, so you don't know what to say. Okay, but at least you know which one is more important. But you can't really say further more than that because you don't really know what's going on. This is a black box. I hope it's clear what do you mean. But let's apply it to the case. Again, Airbnb problem. Okay, the Airbnb problem is, remember the thing, right? They do random forest. Okay, now the same thing to the random forest. So let's see what they do. Okay, they just run it. Okay, and the root mean square error slightly less than OS. Okay, it's 10% less. So if you're happy with that, then yeah, go ahead. if you want to do prediction. Okay. And besides variable importance, okay, there's another plot we call the partial dependence plot. Okay. And in that one, it looks like, okay, regression coefficient. Okay. As to tell you if that particular I changes, how other changes. Okay. It can look like any shape because the random forest idea is like flat, 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 right? But it's average, so, but still, you can see something. So this is the variable importance plot, okay? And you can see in this example, not surprisingly, and the first one is most important is N is number of comma days, is how many people can live in this flat, right? That actually mean the area somehow. The second one is also very interesting, is how many rooms you have, right? The more room, more expensive, not surprising. The third one is number of bed, also makes sense, right? More bed, more expensive. The third one is bathroom, okay? How many bathroom? That is also very good, okay? From that on, yeah, it's where the location, right? It's Bothwell and Westminster, and how many days there have been listed, and so on and so forth, right? So this is the random forest give you, and you can see, at least you know what are the important variable. Okay, that is still a black box, but you still need, you will see what features are there, right? At least you will try to make sense of that, right? There's where iron is there, sample is here, right? There's a bunch of variable there. Okay, and this is somewhat complicated. What the book said is focus on top 10, which is more fun. Okay, but at least you would know what can be seen from this table. And here is the PDP plot. Okay, the PDP plot looks like this, right? It looks like regression. Looks like if you go accommodation from this to this to this to this is what I have. Okay, but it's not entirely clear. It's just average, right? So it's not entirely clear what you expect. And this one looks like this. Okay, you don't know what to say, but at least you would able to see what's going on. Okay, and here is the model. Okay, and here is like what they do is they still also standard way to do is if you have a model, as you can see, the most important part is type of the room and how many accommodates, right? So that is the standard thing is you try to look at different apartment, different location, and different apartment size, and do machine learning within this subset of sample. Let me repeat what I said, okay? Because look at the variable importance, right? The first three items is the size, the type, and the location, right? So you just look at the subsample each, right? Then you do machine learning again. Is that clear? Then you can see whether your model improves, okay, how it changes, right? The overall is all here, right? And then you can see how your model fit, okay? Of course, that will be different in this, right? They run random forest for each one, right? So it's, I don't know how you can compare, but at least you can see how you predict the things. Okay, is that clear what they're doing? Is that okay? So now we cover it very quickly the last one. Okay, it's called the boosting method. They call the GBM, the gradient boosting method. Okay, and the gradient is actually how you build a tree. Okay, the gradient is same as the numerical method. It's called the ladder slope. Okay, but anyway, you don't need to worry about it. But just like, as I said, you grow tree one by one instead of randomly growing many an average. Okay, and the book won't even tell you what it's doing. Okay, so I'm not going to tell you what you're doing. Okay, and do I have the slide? Oh, I don't have the code. Maybe I should add it back. It should be, I mean, I can put the Python code back to here, but it's not something complicated. Just copy GM and just there. Okay, and here you can see there are all the rule here. Okay, ORS, LISO, CART, and random forest. There's some tuning method and the GBM. Okay, you can see actually regression is not that bad, right? LISO is actually surprisingly not so bad as well, right? I mean, of course, you use machine learning method actually reduce a little bit, right? But do you want to do that? The question is, because of LISO or regression is very simple, right? I mean, you know what's going on. You have the regression, you have the coefficient. It's easy to understand. But if you go from here, it's unclear. Even the regression is actually worse off, right? The random forest and GBM is okay. Okay. So this is a summary method. Okay. In the case, you can see regression so fast, right? Just a few seconds, right? And LISO slightly more, right? Within a minute, and CAR is also. But when you do random forest, it's like crazy. 20 minutes, okay? And this one, GBM, is like, I don't know, take several hours, right? But how much gain? Yeah, somewhat, but not too much, right? And which one use? I don't know, right? And you can see the solution, right? Chloroform solution, but these are algorithm solution, right? And ORS, there's no parameter to tune. This one you maybe need to tune. This one is very difficult, right? Interpretation, these three are easy because you can look, right? And these two, not sure. I mean, it's random forest. You don't actually know how I mean, you can look at the code to see there are multiple trees there, how weights are assigned to each tree. I mean, but still it's not clear, right? And you can see LISO and ORS is mainly by hand. LISO is variables led by algorithm. And from that on, everything is by algorithm. Okay. And you probably ask, the last question would be, what you should do when you do a project if you want to do prediction, right? Then you do 5 or 3 or 4 of them and compare, right? That's what you do, right? You don't manually pick it, right? You look at this and see, in this case, how will I pick? I probably pick LISO, if you ask me, right? Because not the lowest, but it's fast, it's simple. I can easily interpret. I can tell other, okay, this is my result. I mean, or I might even go to ORS, right? Because ORS, although has higher root mean square error, but we know very clear what's going on. What we are minimizing, what we are doing actually is very well studied. So unless a big improvement, now it's only 5%, probably I'll go ORS or LISO. So I'm not going, but of course, it's just a matter of taste, okay? Because it's a prediction, right? So it's not really the hard and fast to tell you what. But you probably have to convince your boss or your co-author, co-worker, right? Which one is better? But to me, I anything is fine, right? If you ask me, okay? But I will not go for this guy, right? GBM is like, I'm not, this cost is too much, right? Maybe random forest I still can accept, but you can see the time, right? But anyway, that's all for today. Have fun for your Halloween.